Our final topic for the chapter is buffers. Now, a buffer is a solution containing a weak acid or weak base and its conjugate acid or base to form a solution that resists changes in pH. And buffers are really important in lots of areas of chemistry and show up all the time in acid-base equilibria that we're thinking about. So a solution that resists changes in pH. Some of the most important buffers that exist are biological buffers. So your blood is buffered to make sure that the pH stays in a consistent range that your body can deal with. We use buffers a lot in biological experiments to make sure that we have a good environment for cells that we're growing and things like that. And so buffers are a really important topic for many of you that are studying biochemistry because our biological systems use buffers all over the place. And so here we're thinking about a buffer as a combination of a weak acid, or we can think of this as a weak base, and its conjugate base. So when we mix them together, we essentially get whatever we mix together. There's essentially no reaction that happens. If we think about a combination of HA and A-, we're going to keep this generic to start with, and we'll look at some specifics in a little bit. If we put those together, we'll get these reactions that happen, right? We'll get dissociation of HA into H plus A-, and we'll get A- plus water reacting to form HA, again, plus hydroxide. And so as these reactions are happening, right, we know Ka is small because these are weak. By definition, each of the equilibrium constants has to be small. And, if we are producing H plus, for example, here, or A-, that's going to push, each of these reactions are not a lot's going to happen here. And so we can kind of think of when we mix together a solution of HA and A-, our concentration of HA will be about equal to what we start with. And same thing for the concentration of A-. Okay, so the question here, though, is how do we find the pH of a buffer, and how do we understand its buffering capacity, right? How much can it resist changes to pH? And so the equation that we use to find the pH of a buffer is what is known as the Henderson-Hasselbalch equation. Henderson-Hasselbalch, there's an L in there though, equation. And we'll go through where this equation comes from. And essentially this equation is a rearrangement of the Ka expression. So we know that Ka is equal to the concentration of H plus times concentration of A- divided by the concentration of HA. That's just the definition of Ka that we've been using. So let's take the log base 10 of both sides. So we'll get log 10 of Ka is equal to the log of this whole fraction. All right, and now we can start using mathematical definitions here, and this is also base 10, to rearrange this equation. All right, so log of Ka, we'll keep that the same, log 10 of Ka. And when we have fractions inside of a logarithm, things that multiply, we can add those together. If we divide things, that gets subtracted. So we can separate this out into a log base 10 of H plus, and we'll actually keep this other fraction together. Plus, because when we're multiplying things inside the logarithm, they get added together out if we separate the logarithm, plus the log base 10 of concentration of A- divided by concentration of HA. All right, now let's swap sides for this term and this term. So we'll have negative log 10 of H plus And now that should look like something that we're interested in. It's equal to negative log base 10 of Ka plus log base 10 of our same fraction that we have here, concentration of A minus over concentration of HA. And now we can use the definitions here of the p-values. pH is equal to pKa plus log base 10 of A minus over HA. And this is the Henderson-Hasselbalch equation right here. So we can see this is just taking logarithms and then rearranging things. So it is basically, it is the Ka expression just written in a more convenient form. But the key here is if we know the concentration of our conjugate acid and our conjugate base, we can plug this directly into this expression here. We can rewrite this also in terms of a base and get a equation in terms of, right, so we can say pH is equal to pKa plus log base 10 of concentration of B over concentration of BH plus, and the Ka is for the conjugate acid that goes into this expression. All right, so in the next videos, we'll look at applying this equation.